Hello guys, welcome to this video series on linear algebra for engineers. In the last video, we talked about ways to form new subspaces out of given subspaces. And one of the ways to do it is sum of subspaces. And a particular case of sum of subspaces was direct sum of subspaces. So direct sum of subspaces. And we also saw that union of two subspaces need not give us a subspace, whereas intersection of two subspaces always gives us a subspace. So this was the content of our last video. The current video is going to be about matrices and and some formula based upon direct sum and sum of vector spaces. This will be the content of today's video. So let's quickly start this. So let's note a result which says that if u1, u2 are two subspaces of V and V is a finite dimensional vector space, then dimension of u1 plus u2 equals dimension u1 plus dimension of u2 minus dimension of u1 intersection u2. You must have noted few short videos which I've uploaded that are using this formula to solve problems. Okay. Now, if if it's a direct sum, is if it's a direct sum, then we know from our last video that this is equivalent to u1 intersection u2 being a zero space, right? So u1 plus u2 equals to direct sum if and only if u1 intersection u2 is zero space. We saw that in the last video. Now, zero, the zero space is said to be spanned by the empty set, and empty set is considered to be linearly independent. So, what will be dimension of the zero space? Well, empty set has no elements inside it, so zero, right? That is, we say that empty set spans the zero space, or empty set is a basis of the zero space, right? A basis with zero elements in it. Therefore, dimension is zero. So in this case, what happens to this formula? Well, this becomes dimension of u1 direct sum u2 equals to dimension of u1 plus dimension of u2, and this term is zero. So we get this formula. Okay, let's solve a problem based upon this. It says that if U and W are two subspaces of R8 such that dimension of U is 3 and dimension of W is 8 and U plus W equals to R to the power 8, then prove that U direct sum W is R to the power 8. Okay, so let's solve this quickly. We apply this formula. This is also known as the dimension formula. So let's apply the dimension formula here. Dimension of U plus W equals to dimension of U plus dimension of W minus dimension of U intersection W. What is this? This is dimension of R8, which is 8. This is 8. And this quantity is 3. This quantity is 8 minus dimension of U intersection W. This gives me dimension of U intersection W equal to 0. But this means that U intersection W is just the zero space, and we know that this is equivalent to U plus W equals to U direction, right? So this proves the result. This is given to be R to the, this is given to be R8. So we are done. We are done. Okay. Now let's move on to matrices. So what is a matrix? You already know what a matrix is. So it's nothing but a rectangular arrangement of numbers, right? Like for example, 1, 2, 3, 4, 5, 2. It's a matrix. So it has two rows, right? Row 1, row 2, column 1, column 2, column 3. So it has two rows and three columns. Similarly, if you look at this, 2, 4, 5, 4, it has two rows, 1, 2, and two columns, column 1, column 2. So it has two rows, two columns. See, it's basically arranging numbers in a rectangular fashion. Okay, so these are matrices. And if we denote a matrix by A, let's say this is 1, 2, 3, 4, 5, 6, 3, 2, 1, then we denote this element by small a, I, j. I represents row, j represents column. So aij means element at the intersection of ith row with jth column. Okay, so let's write a12 means element at the intersection of first row with second column. So this is the first row, this is the second column. Here we're intersecting, so it is 2. And what is A13? Intersection of first row with third column. First row, third column. One. This is one. And what is A22? Second row with second column. Second row, second column, second row, second column. So this gives me 5, and so on. And we denote matrix A sometimes like this: Aij, and it's 3 by 3 matrix, 3 rows, 3 columns, right? So if A is m by n matrix, this means that A has m rows and columns. Okay, so let's do a quick problem exercise. Matrix A Ij, let's say it is 4 by 4 matrix, and Aij is given by I plus j. Okay, then what is Aij? What is this? Well, let's make it slightly simpler: 3 by 3, so that this becomes 3. So one way to do it is by writing the matrix A explicitly. So what is A11? So here we'll have A11, that is first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, and 3 1, A 2, A 3. Just write out all the elements. What are all these elements? So A11 is 1 plus 1, 2, 3, 4, 3, 4, 5, 4, 5, and add everything. Just add all these elements. Add all these elements. And what's the answer? Gives me 9. 3 to 5 plus 4, 9, plus 3, 4, 7, plus 5, plus 9, plus 6. And what is this? This gives me 36. So 36 is the answer, right? Another way is to do it just algebraically: I plus j. So first, let's take I. What will happen? So we have this I from 1 to 3 plus j, I is from 1 to 3. So this is 1 plus 2 plus 3, that is 3. 3 plus 1 by 2. This is just 1 being added to itself 3 times. So this gives me 3j. Now j here. And this is what? 6j plus this 6 times j, 1 to 3 plus 3 to 6. Right? This gives me Same thing, 36. Okay. And Aij is called ijth entry of A. Okay. Now, how do we add two matrices? So, if A and B are two matrices of the same order, that is, both are m by n, then A plus B is nothing but Aij plus Bij m by n, right? That is, you add them term by term. So the result A plus B is also an m by n matrix. Let's see this through an example. Suppose A equals to 1, 2. So it's a 1 by 2 matrix. And B is equal to 0, minus 2. This is also 1 by 2 matrix. One row, two columns. So what is A plus B? It will also be a 1 by 2 matrix. Add term by term. So 1 plus 0, 1. 2 minus 2. That's it. So this is addition of matrices. Similarly, we can define subtraction of matrices, right? Okay. Now, how to multiply a matrix by a scalar? So C times A equals C times Aij m. That is, still the matrix remains m by n matrix, and all the entries are multiplied by C. Let's see how. So 1, 2, 3, 4, for example, and you're multiplying by 2, then this will give you 2, 4, 6, 8. Multiply everything by 2, and that's it. Now, if I denote by this symbol the set of all 2 by 2 matrices with real entries, that is, iota and all are not allowed, then can I say that M2 by 2 R is a real vector space, right? Then you'll ask me what are the operations? Well, I'll say operations are matrix addition, this addition that we have defined here, and scalar multiplication is this. The answer is yes. As you can check, and you should check, it is a vector space, right? Now, what is the dimension of this vector space? Can you tell me the dimension of this vector space? What is dimension of Let's try to find out. So suppose ABCD is a matrix inside M2 by 2. Then I can write it as 1 0 0 0 plus B plus C plus D. Okay. Now note that these, let's denote it by E11, that is entry at 1 1 is non-zero, and let's denote it by 1 2 denoted by 2 1, that is entry at second row and first column is non-zero, and denote this by E22. Then it is obvious that every element in M2 by 2 can be written as linear combination of these vectors, right? That is, I can say that M2 by 2 R is a span of E11, E12, E22, and E21 and E22. Right? But are these linearly independent? You can check that E11, E12, E221, E22 are linearly independent. Okay, so why is it that? It's easy to check it. So let's write C1 plus C2 plus C3 plus C4 equal to 0. This 0 means 0 matrix. Okay, now what do you get? Simplifying all these, you get this equal to the 0 matrix. Compare and you'll get C1 equal to C2 equal to C3 equal to C4 equal to 0. So all these coefficients are 0. Therefore, they are linearly independent. So even one, even two, E21, E22 are linearly independent and they span this vector space. Therefore, they are basis. Right? So E11, E12, E21, E22 is a basis of M2 by 2 R. And therefore, what is the dimension of M2 by 2? It's 4, right? Dimension of this is 4. Okay. Now, how do you multiply two matrices? Suppose you have a matrix A, which is M by N, and you have a column vector, say X is a column vector, which is N by 1. That is, it has only one column and N rows. That is, it looks like something like this. Say 1, 2, 3, 4. Right? And how do you multiply these? Let's see. 6, 3, 5. Oh, let's multiply in general. Suppose you have A, M by N, and you have B, which is N by K. Then AB is it's a it's an M by K matrix. Okay? That is, you cancel this N and you get M by K. So it's an M by K matrix. And what are the entries of it? Let's do that through an example. So it's a 2 by 3 matrix. Therefore, here we need to have 3 by something matrix. Let's say it is 3 by 2. Then we have 1 0 0 1 1 0 1 1 1. Then this will be a 2 by 2 matrix. Let's see what are the entries. First, we need this entry, 1/1 entry. To get 1/1 entry, take first column, first row from here, and first column from here, and multiply them pointwise. That is 1 1 2 0 3 0. Okay, and add it. So you get so 1 1. That is you're taking this and this. We're trying to produce this. Okay, this is A11. What is A11? First row of first matrix, first column of second matrix, then multiply them pointwise. So 1 into 1 is 1, 2 into 0, 0, 3 into 0, 0, this is 1. So A11 is equal to 1. So we'll write 1. Now how about this? This is A12, this is first row, second column. So we take first row from here, second column from here, and multiply them pointwise. 4 into 0, 0, 1 into 1, 1 into 1. So you get 2 here. And how about this entry? This is A21. So, oh, wait, we made a mistake here. So, A12, first row from here, second column from here, right? And then multiply them pointwise, you get 1 0 0, 2 1 2, 3 1 3, and you get 5. A21 is second row, first column, multiply, you get 4. This is, and what is A22? Second row, second column. So, 4 0 0 plus 1 plus 1, you get 2. So, this is the result. Okay, so this is 3 by 3, right? Or let's make it like this. Fine. All right. So I hope matrix multiplication is also clear. Let's try to do this one. This is 3 by 3. This is 3 by 1. So we should get 3 by 1 here. And what kind of entries does it have? It has A11, A21, A23. Let's write A11. What will be A11? It is the first row, first column, and multiply pointwise. You get 1 plus 2 plus 3. This is 6. A21, second row, second column, multiply pointwise. You get 3. A23, oh, A3, 1, third row, first column. So you get 2 plus 2, 4, right? So it's really easy. Note one thing. Isn't this same as 1 into 110 plus 1 into 212 plus 1 into 312, right? This addition gives you this vector. Okay, let's take another example. Say 1, 2, 3, 4, and you have 1, 2. What do you get? 2 by 1. What is this entry? First row, first column. First row, first column. Multiply. Get. Similarly, here you get 2 plus 8, 10. Again, note that isn't this same as saying this? This is also same as this quantity. So what is happening here? Whenever we have a matrix A, say it is m by n, and this B, or let's call it x, it is n by 1, that is the column vector, then this is actually a linear combination of columns of A, right? You can see column 1 is here, column 2 is here. So this is a linear combination of columns of A, right? And this is equal to this. So this gives us a linear combination of columns of A. Okay. Now let's note some definitions. So if A is an m by n matrix, then if we look at the span of columns of A, then this gives me a vector space, right? So span is a vector space. So I'm taking span of columns of A. So this vector space. Okay, so this is a subspace of what vector space exactly? So columns m by n. Columns are here, right? So columns are basically m by 1 vectors. So span is actually a subspace of Rm, right? So a subspace of Rm. So A, A m by n matrix has a vector space associated to it given by this. And we call this column space of A, right? This is column space of, okay. Similarly, we can take a span of rows of A, and we call that row space of A. So row space of A means span of rows of A, and column space of A means span of columns of A. Okay. Now let's take a look at this matrix. This is a so-called identity matrix. It's a 3 by 3 identity matrix. What is column space of identity matrix? Span of 1 0 0 0 1 0 0 0 1. And you know what this span is. This is nothing but R3, right? And what is the dimension of this now? It is equal to dimension of R3, and dimension of R3 is 3, right? So let's note the definition now. So dimension of column space of A is called rank of A. This is the meaning of rank of a matrix. And there is a result. It says that dimension of column of A is same as dimension of row space of A. Okay, this is the result. Dimension of row space is same as dimension of column space. So what is rank of I33? Well, rank of I33, that is rank of identity, is nothing but 3. Okay. Similarly, what is the rank of this matrix? Rank of this is nothing but dimension of column space 1 0. And what is column space? Column space is span of columns. And this is nothing but R2. So rank of this is 2. Okay. So let's stop here and we'll discuss the remaining concepts in our upcoming videos. Thanks so much for watching this video. Please like, share, and subscribe. Bye bye and take care.